All right, let's continue from where we left off last time. So, this is the second of three lectures we're going to be doing on P and NP. So, the first one, we introduced these two classes, P and NP, where P is deterministic polynomial time, and NP is, as you remember, non-deterministic polynomial time. And another way we could phrase NP is the set of all languages with polynomial time verifiers. And because we had a few classes that were canceled, obviously, we don't have as much time to get into why this is the case, but it turns out that you can prove that these two definitions are equivalent to each other. And it's actually a lot more convenient to talk about the second one than the first one in most cases, because if you have a verifier, then that machine runs deterministically, and if you can show that there's a verifier that runs in polynomial time, then you don't even need to worry about non-determinism. So it's a bit easier to talk about. So the big open question that is not resolved, and we're certainly not going to resolve in this class, is whether P is equal to NP or not. And the motivation for asking this question is the P problems are the ones we can solve quickly, in some sense quickly, and the NP ones are the ones we can verify quickly, right? Because they are all languages with polynomial time verifiers, and P is just the ones that you can just solve directly. You don't even need a verifier for it. And in fact, even if you have a verifier, you can just ignore it because you can just solve it in polynomial time anyway. So what can we say about this? Well, the belief is, for most people, and by most people I mean sane people, is that P is not equal to NP. So this is not proven, but there's a very large amount of evidence to suggest that P is not equal to NP. So, well, let's just assume for the rest of this class that P is not equal to NP. Then, from that, what you may be asking, okay, what would be an example of some language or problem L that's in NP but not in P? So what would be an example of some language that has this property, assuming that they are different? So if they're different, there must be one. Then, well, let's see. Well, then if we have that belief, then we have this picture of what these two classes look like. Then what we're asking is, what would an example problem even look like at this place right here? So what we would want to characterize such a problem is to be, in some sense, the hardest problem in NP, whatever that means. So if we can somehow formalize the notion of what a hardest problem actually is, then that would be a good candidate for a problem that is in NP but not P. So there are many formulations that you could take to what hardest actually means here. But one notion that we're going to be looking at is, so what does hardest mean? One hardest interpretation might be, so then if this problem or language, however you want to think about it, if this problem is in P, if it just happens to be in P, then all other problems in NP are also in P. right? So that is some notion of what hardest means, because if we can somehow solve this hardest problem really fast in polynomial time, then it makes sense that all other problems in NP, either at the same difficulty in some sense or less difficulty, then they should also be polynomial time solvable. So that is the definition of hardest that we're going to take here. So how do we formalize a notion like this? So here's what we're going to be talking about here. So it's something called a reduction. So if I can friggin' spell right, polynomial time reduction. So the important word here is reduction. So from two problems, A and B. Actually, I'm going to give them different names because we have the A over here. But let's just say X and Y. So X and Y are two different languages. So what is the reduction? So it is a function f that goes from X to Y, such that if we have some string W that belongs to X, then this holds if and only if the resulting value, if we apply f to this string W, is in Y. So if we have a function where we have a string W in X, but f of that W is not in Y, then it's not a reduction. And if we do have that type of property, but it doesn't run in polynomial time, then it's not a polynomial time reduction for obvious reasons. So why would you want something like this? Well, the reason is that suppose that y was really, really fast to solve. Then what does that tell us? And note that f is polynomial time to compute. So if I give you a w, then I can find f of w efficiently. So why do we want to study this? Suppose that y was efficiently solvable. Then what does that imply about the X language? Well, no matter what input we can get, what we can do is just apply the function f, run the tester for y in polynomial time, then the answer of whether f of w is in y is the same because of this if and only if right here, of whether the original input w was in X. And we'll see examples of this. But the reason for doing this is the answer of whether w is in X is the same as whether f of w is in y. So if y is fast to solve, then X is fast to solve because the reduction, the function itself to compute f of w, takes polynomial time, and the test of whether it's in y, assuming that y is in P, that also takes polynomial time. So the whole thing takes polynomial time. So then that tells us that X is in P. So then if y is in P, then that implies X is also in P. So then what we can say is the contrapositive of this. So then if X is not in P, then y cannot be in P. It's literally just the contrapositive, which is equivalent to the original. And what are we going to say here? Well, we're going to write this in a special way, and I'm going to put it in different colors because it's important. So we're going to write this as x less than or equal to with a subscript p right here, and then y. So this says that x polynomially reduces to y. And I'm not sure why they use less than or equal to here. It should be the other way, or an arrow or something. I don't agree with this notation, but this is just the notation everyone in the entire world uses. So unfortunately, we're stuck with this. But this just means that x reduces to y. So if y is fast, then x is fast. If x is not fast, then y is not fast, for some notion of fast. Okay, so a few more definitions. So we're going to, so I'm going to write definition here. So a language L is NP hard. So that's the term here. If for every, I'll just say x, for every problem in NP, so it really does have to be every, we have that x polynomially reduces to L. So that tells us that if we could solve L quickly, and L is NP hard, then that tells us we can solve every problem in NP quickly because x reduces to L for every x in NP. Every problem in NP reduces to this problem L. So if this is true, then we say it's NP hard. So if we do find an NP hard language, then that's a candidate for a hardest problem. But we gotta amend the definition somewhat by introducing another one. Why is that? One could actually show, that ATM, that famous undecidable problem, is in fact NP hard. And it's actually not too hard to show that, but I won't do that here. So because ATM is undecidable, there's no chance that it's in P or even NP, because those just run in polynomial time, deterministic or non-deterministic. So we got to amend the definition a little bit. So another definition is we have a language L is not NP hard, but NP complete. So then if L is NP hard and L is an NP. So by that reason, ATM is not NP complete because it's not an NP. Because it's not even decidable. So yeah. So if we can find an NP complete problem, let's just make a simple observation here. So if a language L is NP complete, and we find for whatever reason that L is in P in polynomial time, deterministic, then that implies that P is equal to NP. Because if a language L is NP complete, then every problem in NP reduces to this one, and we find that it is efficiently solvable, which means every problem in NP is also efficiently solvable. So that means that every problem in NP can be run in deterministic polynomial time just by doing the reduction and doing whatever algorithm shows that L is in fact in P. So the open question is there such a problem that is NP complete and in P also? And despite decades of research, no one has ever been able to find one, and most people believe there doesn't even exist one. So, but in order to actually determine this, whether a language is NP complete to start with, well, checking whether it's an NP, everyone can do at this point. So that's not the hard part. The hard part, in some sense, is checking whether a language is NP hard. Well, remember that NP hard means that every problem in NP reduces to it. So we could do reductions all day long, but the problem is there are infinitely many problems within NP, and there's no way we can treat all of them. So we're going to take a slight detour to talk about how do you even prove a problem to be NP complete to start with. And Oh, the problem that we're going to talk about that was first proved by Cook and Levin in the early 1970s. So this is 1971. I think Levin did it in 72 or 3 or something, but it's called the Cook-Levin theorem. So their basic result here is there exists an NP-complete problem. So there is an NP-complete problem to start with. One thing that you should always note is that you can define things all day long, but it could very well be that it just doesn't exist. There's no language that's NP-hard or no language is NP-complete. Actually showing that is rather important. Yeah, because we can just make definitions all day long and not actually get anywhere. So what is the problem that they were able to find is NP-complete is something called CNF satisfiability. So they didn't actually do this. In fact, amazingly, if you can believe it, their papers don't even make a notion of what NP is. They never even define the term NP or NP-complete or anything like that. But in our terminology, their problem that they showed was NP-complete. So what is this problem satisfiability? So it's unlike things that we've seen before, but it's actually rather important in the vast majority of domains, including my own research. In fact, everyone's research, I claim, has some relevance with satisfiability. So what is this problem? So we're going to be given input a bunch of Boolean variables, and let's call them x1 up to xn, and we're going to have Boolean operations, and the usual ones. So and we can and two variables, we can or two variables, and we can not a single variable. So the variables themselves can appear in one of two ways. They can appear in positive form, which is xi, just the variable xi, and nothing special, or a negative form, which is basically just applying the not operation to a variable, and that is xi with a little bar over it. And these two things, just by themselves, either a variable in positive form or a negative form, is something called a literal. So kind of like a string literal in programming, these are just Boolean literals. It's just an occurrence of a variable. That's literally all it is. And now the important part, so I can just define variables and operations, and we can compose variables in various ways. But the important thing here is something called a clause. Not Santa Claus, just a normal clause. So what this is an OR of literals. So, for example, we could have, and they are separated by, not separated, but they are surrounded by parentheses. So what could appear? We could have, for example, x1 or not x2 or not x3, just as an example. So the v's here represent ORs, and we have the literals here, x1, x2 bar, x3 bar, but we can also have another clause. And let's just say we have another clause here, x1 bar, or x2, or x3 bar. So again, we just have a clause which is just an OR of literals. Nothing special there, but we're going to connect them. And how are we going to connect them? We're going to put an and in between clauses. So the v here, not the v, the wedge, so this is something called a wedge. This is the and operation. So what we're saying is that if I say that x1 is true, x2 without the bar, just normal x2 is false, x3 is false, then x1 is going to be given value true. x2, if I gave it false, the negation will say that this is true. x3 was false, so the negation said that this is true. So true or true or true, so the whole clause evaluates to true. So then now let's look at the other one. So x1 was true, I think, so x1 bar is false. Then x2 was false, so that means that x2 just by itself is false. So currently we have false or false. Well, x3 bar is going to come save the day because x3 was false, so x3 bar is true. So false or true, if you remember from 101, that evaluates to true. So the first clause was true, and the second clause was true, and so therefore we have true and true. So that means that assignment of true or false to x1, x2, and x3 evaluates to true. So for x1 equal to true, x2 to be false, x3 to be also false. So setting x1 to be true, x2 to be false, x3 to be false makes the formula evaluate to true. And what is this thing? The whole thing is a formula, is literally just an and of clauses. So the formulas that we'll be talking about here are just ors of literals, and those form clauses, and the entire formula is just an and of clauses. And one thing I should note here, it's not required that they all have the same number of literals in them. They can have any number of literals that they want. What we can actually show is that we can whittle this down to 3 in the general case without making the formula too big in some sense. But there's no restriction on what the input is as long as it's in this form. So it's an or of literals and an and of clauses. So what is the satisfiability problem then? So a formula, formula is satisfiable. So the term that we're going to be looking at is satisfiable if there exists some true-false assignment to its variables to make the formula evaluate to true, evaluate to t. And for that reason, the formula we just talked about before was satisfiable because we found an assignment to the variables to make the formula true. And there very well could be a different set of assignments for which the formula is also true. As long as some true-false assignment makes the formula true, that's all that we care about. Okay, so then what is the CNF set? One thing I should say. So whenever we have these ands of clauses in this case, so this is something called conjunctive normal form. So it's not Chomsky normal form. It's just unfortunate that we both call them CNF. You just have to figure out whether you're talking about Chomsky normal form or this normal form. It's just unfortunate, but it's formulas of this type. So, i.e., or, I should make that capital. So an or of literals and an and of clauses. If the formula is in a different form, then we don't, then it's not in conjunctive normal form. And so CNF is the terminology we'll use for this. Okay, so, and there's a special reason why you would want something in conjunctive normal form. The reason is that the runtime is actually significantly faster than if we just had any Boolean formula. So what they actually proved was something more along the lines of a satisfiability problem, where you can be given any formula as long as it's a Boolean formula. So it doesn't have to be an and of clauses. It could be any mix of them. And it can have nested clauses within them and all that stuff. But let's just make this easy because it's easier to understand. So let's talk about the CNFSAT problem. So what is this problem? So I'm going to be given a formula phi. So phi here is a Boolean CNF formula. I know lots of definitions, it's unfortunate. That is satisfiable. Oops. Satisfiable. And what can we say about this problem? Well, CNFSAT is, I claim, in time 2 to the n times n. And why is that? Well, we can just try all possible variable assignments. So the 2 to the n here is all possible variable assignments. And the extra n here that's multiplied here is just the time to evaluate the formula once. The formula once. Per variable assignment. So we make an assignment to the variables, we evaluate the formula, see what happens, and if it evaluates to true, we stop. If it evaluates to false, we just try the next variable assignment and see what happens. So there's no looking into what the formula structure actually is, or taking advantage of the fact that it's in conjunctive normal form. So this actually is the runtime you can use for any Boolean formula of any size, of any type. So CNFSAT, you can actually make this significantly faster because the formula has a specific structure to it. But we're not going to talk about that here. So, so let's talk about what types of classes it's in. So CNFSAT, I claim, is in NP. So it's an NP. Well, so the thing we should always ask whenever we're given a question about whether something is in NP or not is to say, what is the, not what, what is the verifier and certificate? So what is the proof certificate? So what is the proof that we're given a formula phi of whether or not it's satisfiable or not? So what would be a convincing argument, say for this formula, whether it evaluates to true or not? Well, the proof would be just giving you the variable assignments. So if I give you all the variable assignments, then you could verify whether or not it evaluates to true. So the certificate here is the variable assignment. And what does the verifier do? So on input a Boolean formula phi, then check if the assignment satisfies the formula phi. And then if yes, then that means we should accept, otherwise reject. So pretty straightforward. Yeah, so the certificate is just the proof of whether or not a formula is in CNFSAT, meaning that it's satisfiable, and the verifier just checks whether that assignment really does satisfy the formula. And you can do that in polynomial time because you don't have to go through all possible assignments, which is what this part is saying. We just have one assignment to check, and the time to evaluate it is n, the size of the formula itself, and that clearly is in polynomial time. So the verifier runs in polynomial time for that reason, and so therefore, because NP is the class of problems that run that have polynomial time verifiers, that tells us that CNFSAT is in NP. But just because it's in NP doesn't imply that it's NP complete. So what did Cook and Levin do? So this is the can't write. So this is what Cook and Levin showed, which was that CNF Set is NP complete, meaning that they showed that CNF Set is really NP hard. So they showed it is NP hard. And the reason why this is difficult to do, and why it took an entire paper or 2 papers to do this, was that there's no NP complete problem to start with, so you need to show that any problem in NP can be reduced to CNFSAT. So I'm just going to give a proof sketch, because the proof is very easy to understand, but it requires a ton of technology and lots of little details. And if you're really, really interested, look at Chapter 7 of CPSR. So this comes from Chapter 7 of CPSR. For all of the gory details of this. So what do we want to do? We want to show that every x in NP reduces polynomial in time to CNFSAT, because that's what the definition of NP hard is. So let's see. Well, we don't know anything about x other than the fact that it's in NP. So what do we know? We know that x has a poly time verifier. But the problem with doing the verifier's viewpoint of NP is that what is the certificate in this case? So we don't know anything about x other than it has a verifier, but we don't know what the certificate is, so we can't really understand what how that actually plays a role in what the verifier really does. But the other definition of NP comes to the rescue, so that because it's in NP, that means that there is a non-deterministic polytime Turing machine. So x has a non-deterministic, I should put it next to this because that's not the viewpoint you should take. So it has a non-deterministic Turing machine, M, running in polynomial time. So what is the idea? So their idea was to build a formula that is satisfiable if and only if we're given a string w that is in x. So if we're given a string w, then I'm going to make a formula, and the formula is satisfiable if and only if w is in x. So the function f, which is the reduction, takes the... I should actually write this out. So what is the reduction here? Take take a w as input and produce a formula in polytime, such that W is an X if and only if the formula is satisfiable. Okay, well, that's literally what a reduction is, and as long as it runs in polytime, then we're good. Well, the only thing that we know about W is just as it's an input to this Turing machine M up here. So what we do is we're going to make the formula. What it does is it tracks the accepting computation history of M on W. And what does this formula have property? So what's the property of this formula? It is satisfiable if and only if there is such an accepting computation. Okay, so that's the basic idea. And the formula involves a whole load of variables and clauses. And so what are the clauses in this sense? So actually, before I get to the clauses, I should say what the variables are. So the variables, essentially, so I'm lying a little bit, but they're basically saying in what configuration and each cell of this configuration. So in each configuration, in what configuration and every cell of each configuration, what tape cell is there. So in some sense, what we could do is say x1 to q0. So this is the type of variable you'll see if you look in the proof. Well, what this is communicating to us is that the 1 here represents the first configuration. The 2 here means the second cell. And q0 is the value in that cell. So if you visualize what the configuration looks like, then it's some value first, which is, let's say, because it's in the second cell, there must be something before it. So maybe it's like blank, and then q0 must be in the second cell, then maybe w3, w4, etc. So something like this. And we can build this formula in polynomial time because the Turing machine that we are given here also runs in polynomial time. So that means that the number of configurations that we could ever have is polynomial in size. But you may think, okay, well, the number of configurations is polynomial, that's fine. But how long are these configurations? Because we have to communicate what each cell of each configuration looks like. Well, we're actually in luck here because the Turing machine can only move right one position every time. So the length of each configuration is at most a polynomial in the length of the input. So that tells us that the number of configurations is polynomial. The size of each configuration is polynomial. So that means that the number of variables that we're making here is polynomial. So the number of variables is polynomial. But that doesn't tell us the number of clauses, because I can just make any old clauses that I want and make exponentially many clauses, or even have duplicate ones and make infinitely many clauses if I wanted to. So what do we want here? Well, it's kind of like the accepting computation history when we did like the emptiness of LBAs or something. So what are the clauses here? Well, we're going to have a clause for the first configuration must be the start one, the start config. So that always must be true. The last config must be an accepting one. And the third one is whether or not the ith configuration yields the I plus first one. Okay, so that's just literally what an accepting computation is. You gotta start correctly, you have to have an accepting at the very end, and every configuration must yield the next one along the way. Okay, so, and actually we need a fourth one. We need that exactly, so this may seem a little weird, but exactly one value per cell. So what do I mean by this? So if we go based off of the formula that we had up here, the variable we had up here, it can't be the case that I have x12 q0 and x12 pound sign both be true. That cannot be the case because they're referring to they're referring to the same configuration and cell, which means that we can only have one possible value there. So it cannot be the case that both of these are true. So I should say here, cannot both be true. It could be that both of them are false, but it can't be both of them are true. And what you're able to show here is that the number of clauses is also polynomial. And it's really important that we talk about polynomial time reductions, because if I just let the reduction take any old time, then if I just say, okay, you can run an exponential time, well, based on the result we had up here, I could just run the formula deterministically in polynomial time. Forget the reduction business. So the polynomial time reduction is actually quite important here. So as long as we can make the clauses correctly, and there's a lot of details there, this implies that x, the problem that we talked about that is in NP, just some arbitrary problem, reduces polynomially in time to CNFSAT. And since x was any old problem in NP, and this holds for every problem in NP, this implies that CNFSAT is NP complete. And what we're going to look at next time is how do we get other problems to be NP complete? Well, the good thing is, as long as we have an NP complete problem, like we do with CNFSAT, then it's easy to prove, much easier than this, to prove that other languages are also NP complete. So I'll see you then.